through one example of what we're talking about. We have a problem here. Let the region be bounded by the lines. The region R is bounded by the lines x minus 2y equal to 0, x minus 2y equals minus 4, x plus y equals 4, and x plus y equals 1. If we wanted to try to depict this region in the xy plane, it would probably look something like this, something kind of diamond shaped maybe, where the lines x minus 2y and x plus y are the lines that connect to form this rectangle. So this is in the xy plane, and we'd like to transform this using a change of variables and integrate the function 3xy with respect to the area. So I'm going to call my change of variables u and v, and I think that a nice substitution to use would be u equals x plus y and v equals x minus 2y. Those are coming, of course, from these. And so right away I can see that my bounds for u and v are going to be, for v, from 0 to -4, from -4 to 0, rather. So if I'm thinking about the uv plane, my bounds for u are from 1 to 4, so from 1 to 4, and my bounds for v are from 0 to -4. So it seems like we're going to have this rectangle once I make the substitution. So I know how to set up my integral with the bounds. I know how to make my substitution, and the only thing that I need to remember is to multiply by the absolute value of the Jacobian. So if u is equal to x plus y, then my Jacobian is the determinant of the matrix del x del u. So I'm going to need to solve for x and y in order to find these, and then del x del v. So I'll have u as a function of, x as a function of u and v, and y as a function of u and v, and I'll find the first partials of x and y with respect to u and v. So let's try to solve this system of equation for x and y. So it looks like if I do u minus v, then I get x plus y minus x plus 2y, and that's 3y. So u minus v times 1/3 is equal to y. And what if I multiply u by 2? So 2u, and I add v, then I would have 2x plus 2y plus x minus 2y. Minus 2y and plus 2y cancel, so that's equal to 3x. So then I can say 1/3 of 2u plus v is x. So I have my expressions for x and y. So now I have what I need to find these derivatives. So this Jacobian will be equal to the partial of x with respect to u is going to be 2/3 is what it looks like. The constants in front of u will be 2/3 if we multiply. And del x del v should just be 1/3. Del y del u should be 1/3, and del y del v, it looks like should be minus 1/3, according to my substitutions. So then If I find the determinant of this matrix, it's minus 2/3 times 1/3 minus 1/3 times 1/3. So I get minus 2/3 minus 1/3, rather minus 2/9 minus 1/9. And when I combine like terms, that's minus 1/3. So the absolute value of my Jacobian is going to just be positive 1/3. And now I think I have everything I need to set up my integral. So I think I'm going to integrate with respect to v first, although it could make a difference, I guess. So let's integrate first with respect to v. And I said that my bounds for v were going to be -4 to 0. My bounds for u were 1 to 4. My function is 3 times x times y. So that's 1/3 2u plus v times 1/3 u minus v times the absolute value of minus 1/3 del v del u. So this should be integration from 1 to 4, integration from -4 to 0. I'm going to have 1/3, that's going to cancel with the 3. Then I have another 1/3 times 1/3 is 1/9. Let's pull that out front. 1/9. So then I have 2u plus v times u minus v dv du. And that should be 1/9. Integration 1 to 4, integration -4 to 0, 2u squared plus uv minus 2uv is minus uv minus v squared. So now I'm ready to start taking antiderivatives. I'm first going to take antiderivative with respect to v, so I'm going to treat u's as constants. So this will be 1/9 times the integral from 1 to 4. My first term, 2u squared, is a constant, so that becomes 2u squared v, minus u v squared over 2, minus v cubed over 3. And I want to evaluate between 1 and 4, between -4 and 0, I'm sorry. And then we'll integrate with respect to u once we're finished. So that's 1/9. Integration 1 to 4. Plugging in 0 for v, I'm going to get 0 everywhere. Then I'll subtract and plug in the lower bound of -4. So this is 2u squared times -4 minus u times -4 squared over 2 minus -4 cubed over 3. So that's 1/9, integration 1 to 4. -4 times the negative outside is positive, so I get 8u squared. Then I have -4 squared, so that's 16. Divided by 2 is 8, so minus 8u. And then I have -4 cubed is 64, and that becomes positive. -4 cubed is -64. I multiply by another negative, I get positive 64 over 3. So 1/9. I'm ready to take my antiderivative with respect to u. So this becomes 8u cubed over 3 minus 4u squared plus 64 over 3u, evaluated between 1 and 4. And that's 1 over 9. 8 times 64 over 3 minus 64 plus 4 times 64 over 3. When I plug in 4, then I'm going to subtract 8 over 3. If I plug in 1, subtract 4, but it's subtracting a negative 4, so positive 4, and then subtract 64 over 3. So I still have 1/9 outside. And to me, I'm going to go ahead and make this 3 times 64 over 3. So I end up having 9 over 3 times 64, which is just 3 times 64. Because I had 8 plus 4 is 12, minus 3 is 9. 3 times 64 plus 4 minus 64 over 3 and minus 8 over 3 is minus 72 over 3. So that's 1/9. 3 times 64, 192, plus 4, 196. And if I wanted to get it over the common denominator of 3, that should be 588, I believe, minus 72 all over 3. Let me just double check that. So 3 times 64, 180, 192 plus 4 is 196, and 196 times 3. Yeah, that should be right. So 588 minus 72, 516 over 27. And can I divide 516 by 3? I think I can. I think I'm going to get 164 over 9. And that should do it. So we used a change of variables to transform this region into a simpler region. So I wouldn't have to set up 2 double integrals. I transformed it into a nice square region or rectangular region. Simple change of variables, and all of the integrals were nice power rule antiderivatives. Get the answer done.